chapter 14, we're not going to be into specifics of chemical reactions, so to speak, like adding more chemical reactions. What we're going to do now is try to understand what the contribution to chemical reactions, organic reactions, is from conjugation and aromatic compounds. The basic concept in the back of your minds here for conjugation and aromaticity is lower energy. Delocalized electron density stabilizes a structure and it lowers the energy. So it modifies the types of chemical reactions that are allowed or that proceed under certain conditions. All right. Remember in chapter 3, we covered the valence bond theory again. And the valence bond theory treats single bonds as sigma, and that is on axis between the atoms. So it's typically the stronger of the two. Pi bonds are overlapping off axis. So a double bond is treated as a sigma and a pi, and a triple bond is treated as a sigma and two pi's. The pi bonds result from overlapping p orbitals. Now we're still in the valence bond theory here. So we're only considering how these bonds are formed, and that is overlapping of p orbitals. And these are useful concepts when we start to talk about conjugated bonds and aromatic bonds, aromatic structures. We can account for a number of important characteristics of molecular structure, particularly using the VSEPR model. But it doesn't always adequately describe how the electrons are delocalized in resonant structures, simply because the valence bond theory says that every atom still owns its own electrons, and it only donates them into overlapping orbitals to share them, unlike molecular orbital theory, which says it's more communist in that way. In other words, the whole molecule owns all the electrons. So we're going to have to make compromises and use aspects of the valence bond theory as far as it'll go before we move over into molecular orbitals to finish the full description. All right, so if we just stay with the valence bond theory, then we can make some predictions about electron delocalization when we consider conjugation of p orbitals. And we're going to have to define what conjugation means in just a minute. We can also think of aromaticity as conjugation on steroids. Aromaticity stabilizes a structure even further than conjugation would have. And aromatics are always ring structures. Okay, I already said that. We're going to try to use molecular orbital theory toward the end to fill in the gaps, so to speak. And we might even introduce, there she is. Carson has arrived.
Sorry, I guess I joined the wrong Zoom link.
Oh, did you go to 211 instead of 212?
Yeah, I guess I did.
Well,
But I'm here.
You're here now, and I'm only on the first slide so far.
Okay, thank you.
Yeah. Oh, by the way, is that a schnauzer?
Yes, he is a schnauzer.
Okay, he had the look.
He's adorable.
Oh, they always are. That's what puppies are for. Okay. Yeah, go ahead.
I was like, well, you can go on teaching.
Okay. um, so the molecular orbitals are going to help us extend what valence bond theory cannot do. And that involves, remember the HOMO and LUMO concepts, the highest occupied molecular orbital and lowest unoccupied molecular orbital. So we're going to get some discussions involving those two. And you'll notice with the handout, you have all those look like p orbitals, some of them white, some of them black. Right? That's just a a taste of what's coming. Now I'm not sure why I stuck these 16, 17. 16 and 17 will be separate. They're for exam 5. So I probably just forgot to pull these out of the discussion. What we're going to do after conjugation and aromaticity is talk about how we actually determine molecular structures and the techniques that are available to us. So today we're only going to cover, and for exam 4, we're only going to cover mass spectroscopy. And then for the next exam, we'll get into chapter 16 and 17, which covers all the what we normally consider spectroscopy, like ultraviolet, visible, infrared types of spectroscopy. Oh, we get into nuclear magnetic resonance too. So that's coming with chapter 16 and 17. But you don't have to worry about that right now, unless you're just super ambitious and you can go ahead and read the chapters. We're going to have to leave out some chapters simply because the course there's not enough time to cover everything, but we'll get as much as we can in. How conjugation and aromaticity affect chemical reactions. All right, there's my typical outline, and we'll just let that hang and move on. All right, remember what an allele group is. An allele has 3 carbons, and 2 of the carbons are double bonded, and the other one's a single bond. That's an allele group. In this case, we're talking about an allele cation, and we've seen these before, and they are particularly when we're involving carbocation reactions. This particular arrangement stabilizes the carbocation by resonance. So it resonates between these 2 carbocations. And if we're stuck with valence bond theory, we have to consider that left hand in the brackets. The valence bond theory says since the electrons belong to each atom, we have to draw unique structures for each one. But we know that the reality is a structure is something in between. We know that because we can measure the bond lengths. We would normally expect the bond length for a double bond to be shorter than that for a single bond, but they're not. They're both the same length. And the positive charge is spread over the molecule. So that's just one of the failings of the valence bond theory, that it doesn't actually give us the true structure. The resonance hybrid looks more like the one on the right. Okay, so if we take this this molecule and we look at the orbitals, what we're seeing is that the overlap of p orbitals gives us the pi bond, and each one of those p orbitals has an unused electron in it. So we get 2 electrons, makes 1 bond. That still holds true. But it doesn't account for the delocalization when we look at it in these terms. In other words, we tend to see things with the valence bond theory as that right-hand structure, where you only get the pi bond on one side, and the carbon has to accommodate the positive charge. It has to be octet deficient. Okay, so this overlap, this resonance structure is more accurate, and that feeds into the concept of conjugation of p orbitals. A set of conjugated p orbitals represents actually a single pi system. In other words, off-axis overlap of the p orbitals is carried across those three carbons rather than flipping back and forth between one single pi bond and another single pi bond on the other side. So the reality is we get a pi system rather than a pi orbital. If we think of it in those terms, then it makes more sense. And we're going to expand on that concept, so hang on to that thought. Another problem with the valence bond theory is if we look at it in terms of that right-hand structure where we have just a single pi bond on the left and a sigma bond on the right, that is less stable because we cannot delocalize the electrons under those circumstances. Resonance doesn't explain the full stability of the, in this case, the allyl carbocation. Oh, by the way, the molecule is planar. That is, all the hydrogens, all the carbons are in the same plane. And that we would not expect if it was just a single sigma bond on the carbocation side. It should be free to rotate, right? But it doesn't. It has pi character, so it's locked in place. Now, the lock is not as strong as a full sigma pi bond between the two atoms, but it still locks it into a planar structure. Okay, so when we're looking for the evidence for resonance hybrids and the pi system that would signify conjugation, each atom in the system has to contribute p orbitals to the system. So it has to have, what that means is it's got to at least be, it can't be sp3 hybridized. It has to be sp2 or, well, actually, no, sp won't work either. Because if it's sp, then that locks out its neighbors. There's no possibility for overlap there. So it has to be sp2 hybridized to have that free p orbital available for overlap. We also have to conserve the number of electrons. The number of electrons in the pi system is the same number of electrons in the delocalized resonance hybrid. So if we're trying to make a pi system, then we look at the number of electrons that are available for the resonance hybrid, where you flip back and forth between sigma and pi bonds on the neighboring carbons. So you have to count the number of electrons there, and those are available for the pi system. All right. So here we have an example, hexa-1,3-dienyl cation. One thing you'll notice is that for resonance structures, double bonds are interspersed by single bonds. If we draw them out as non-resonance hybrids, or as a single version of the hybrid, then we have these pi bonds are interconnected by single bonds, sigma bonds. That's one clue. Now, all right, so we're going to see how many of these atoms can contribute p orbitals. All right. If we start from the left, which is where the name tells us we should start, we have the number one carbon has should be sp2 hybridized. Should it not? Because it has to have one free p orbital to make that pi bond. Number two carbon is also sp2. Number three is sp2, and number four is sp2. Because we can only have four. Let's look at it this way. All right. We have that molecule. That. And we do this, and that, and that. Carbons typically have four bonds to them if they're not charged. This one's charged, so it can only have three. But it will have a hydrogen here. This will have a hydrogen. This will have a hydrogen. And this will have a hydrogen. That carbon. So it's one, let's say, this is two hydrogens. 1, 2, 3. So if we go back to the VSEPR model, remember if you have three groups, 1, 2, 3, that's trigonal planar. And trigonal planar means sp2 hybridized. That's why I'm saying sp2. So this one has 1, 2, 3, 1, 2, 3, 1, 2, 3. So these carbons here, and this one has, this one's also sp2, right? It only has 3. Right? So all of these are sp2 hybridized carbons. That means each one has an extra p orbital that's not used for bonding until we say it is. So if we overlap p orbitals on these two, we get that double bond. Overlap p orbitals on these, we get that double bond. And then we have a p orbital here. It's not going to be overlapped. This one is sp3 hybridized, so it's not involved in the conjugation. It's just these 1, 2, 3, 4, 5. Only the first 5 carbons are involved. And we can resonate the structure like this. We can move the positive charge over to this carbon, the number 3 carbon, or we can put it on the number 1 carbon. And we have those 3 possible resonance structures. But if we combine them into the resonance hybrid, right, the way we do that without is just we say, all right, each one has double bond character. And then we spread the positive charge out all along the molecule. Like that. So to answer the question, which atoms in this molecule contribute p orbitals? Just the first 5. Right? How many electrons are available for this system? Well, this one doesn't contribute electrons because it's deficient by 1. So this one contributes 1, 2, 3. Is it 4 electrons? Yeah. 4 pi electrons are available for this system. And really all we have to do to count up those electrons, I was counting up 1 for each atom, but this pi bond is going to be spread. This pi bond is going to be spread. So that's 2 there and that's 2 there. So that counts up our 4 electrons right there. I guess there's more than one way to answer that question. All right, so we're switching to a different molecule now. this butyl-1,3-diene. So notice that we have two double bonds and a sigma bond in between, single bond in between. So we should expect conjugation for this molecule among all four carbons. All four carbons are sp2 hybridized. And if we look at, let's see, yeah, that's still covered up there. Butyl-1,3-diene doesn't have an atom lacking an octet adjacent to a multiple bond. So we look at it slightly differently, except that it doesn't exhibit the same type of resonance because there's not a deficiency. But it still does undergo conjugation. Right? And this is probably going to tell you what I've already told you before. Even though the central carbon-carbon single bond can rotate, we would expect it to rotate. It doesn't rotate. Rotation is hindered by the conjugation. We're given that single bond some double bond character, and we're taking some of the double bond character away from what we view as double bonds. And that means the molecule is planar. And we look at the difference between ethene, where the double bond is 132 picometers, but in the butyl-1,3-diene, that double bond, the molecules, atoms that we write as having a double bond are longer than we would expect, and the single bond is shorter than we would expect for ethane. Now, the bond lengths are not exactly the same. So what it looks like to me is that the single bond is still retaining a little more single bond character, and the double bond is retaining a little more double bond character than we would expect, because they are slightly different in bond lengths. All right, I already said that, so we'll move on. Okay, how do they conjugate? Well, first of all, we recognize them to be sp2 hybridized. That frees up one p orbital for overlap. And each one of those p orbitals contains an extra electron. So when we overlap the two, we normally would expect a double bond. But since we've conjugated the system, now we're going to spread those 4 electrons over the entire molecule, which stabilizes the molecule. And you cannot get conjugation if the p orbitals are not able to overlap. So if we allowed that single bond to rotate, then those p orbitals would not be lined up for overlap, right? Except for a very short period of time. So we have to restrict this molecule to being planar. Otherwise, you can't get the overlap that's required for conjugation. Okay, let's see. That's not saying anything new. Yeah, we're sort of hedging our bets with that highlighted statement. All 3 carbon bonds have pi bond character. It's just that the central one has more sigma than pi bond character, and the 2 outer carbon bonds have more pi character than sigma character by just a slight amount. But conjugation itself still holds that it stabilizes the molecule. It has a lower energy. Remember, lower energy is more stable, and we get more stable by delocalizing electrons. Okay. So uh, here's an example of a situation where we can, in this system, the carbocation can resonate with the next door pi bond, but it's too far away to resonate with the pi bond on the end of the molecule, right? It's too far away, right? You cannot get pi bond, uh, pi p orbital overlap. That's what I'm trying to say. So we do get conjugation on the second, third, and fourth carbons on the right, but the pi system on the other terminal end of that molecule does not interact with the other system. It's said to be isolated. Okay. All right. Here's an example where we can this molecule undergoes an elimination reaction, and they were wise and they put an I in there with bars on the top and bottom. Looks like an I-beam, so we don't mistake it for something else. But if we hit it with tertiary butoxide, a very strong base, then we can attack the carbon that's attached to that iodine, and it will leave. It not only will it leave, we will also eliminate the tertiary butoxide and cause a double bond to form. Now, one of the driving forces for forming that double bond in this case is the stability of the molecule after the procedure, after the reaction. Because now you have two double bonds that are separated by a single bond, and those conjugate. That lowers the energy and makes that product favorable. Now, we know from other examples where we don't have this possibility, we could have a double bond on the other side of the carbon, but it's not conjugated. So that means that the one that's conjugated is a more stable one, and it's the major product. I think that's the whole point of this slide. Yeah, this is an E2 produced from an E2 reaction. Okay. Oh, okay. Okay. We have tertiary butoxide in butanol. Butanol supplies the hydrogen. Well, actually, no, the first step would be proton transfer, wouldn't it? To end up with an elimination product. So that's not a, well, that's a recipe. That's a reaction. It's not a mechanism. So I'll just leave it alone. Stick to the point. We get two possible products here. The one that's more stable is the major product. And for quantitative evidence, we go back to a previous chapter, I can't remember which one it was, and talk about the heats of hydrogenation. Right? If we test the heats of hydrogenation for the first molecule versus the second molecule, then since the first molecule is at a lower energy state, it's going to give up less energy when we hydrogenate it. Whereas the higher energy one, did I have that backwards? We're at a higher energy and we hydrogenate it, they're going to end up at the same place. Yeah, it's going to give up, the right-hand one's going to give up more energy, and we can measure that heat. Whereas the one on the left is going to give up less energy because it starts at a lower energy position. Yeah. Took me a second. All right. So the species depicted here, we have, it's probably going to make a liar out of me too, because I see a triple bond. Yeah. So triple bonds can be involved in conjugation. I thought that was a no-no, but I guess if you have p orbitals that are available for overlap, then you can get that. So we have first the depiction of resonance hybrids, resonance structures, using the valence bond theory. And by doing that, we produce, it looks like a conjugated system between the first, second, third, and fourth carbons. But we also have another double bond that allows us to overlap more p orbitals. So this entire molecule should be resonance stabilized, even with an sp2 hybridized carbon. Okay. It has two separate pi systems, okay, even though it has no tetrahedral carbons. That's right, there are no tetrahedral carbons there. All right. Three carbons on the left are sp2 hybridized. All right, that makes sense. Each contributes one p orbital. Two carbons on the right are linear and sp hybridized. Each of those has two p orbitals that are perpendicular to each other. So only one of those, the one pictured in blue, is used for the conjugated system. So we still have a standalone double bond on those the right-hand terminal carbons, and they contribute p orbitals into the conjugated system. Okay, so that makes sense, right? I'd had to convince myself. All right, here's the rule. Only one pi bond can contribute p orbitals to a conjugated pi system. And that's because they have to be in the same plane. Those pi orbitals must be in the same plane in order to resonate. And the green, in this case, the green orbitals are not parallel to the others, so they can't contribute. Right now it makes sense. You can tell it's been a while since I looked at this slide. All right, heats of hydrogenation. Are we going to beat this horse again? The enthalpy change that accompanies the addition of hydrogen to, or did we not look at this before? I thought we did. Didn't we get heats of hydrogenation before? When we talked about double bonds? Maybe not. Okay. All right, so maybe we better spend some time on it then. What we mean by heats of hydrogenation is this is exothermic reaction. So the fully hydrogenated molecule is going to end up at a certain energy level. So if we draw our energy diagram here, then we have, we're going to end up over here with the same product. Right? But where do we start here? Right? Lower energy is going to be the conjugated system. So let's say that one's there. So this is the conjugated system. And this is the non-conjugated system. Right? It's at higher energy level. So we're going to have a certain amount of activation energy there. I'm not sure how this one goes. It probably won't go all the way up there, but it may go up like this and end up down here. So we have different activation energies for the two. This one probably takes less activation energy than that one. Well, if we're going to end up at the same product, and that's what we see there, 1, 2, 3, 4, 5, 6 hexane. then the difference here for the non-conjugated is going to be that value, and for the conjugated is going to be this value for the conjugated system. So the conjugated system should produce a lower heats of hydrogenation. Now, how do we do that? Well, we could do it catalytically, right? Use a platinum or palladium catalyst. And that would make the reaction go faster, but it wouldn't change the outcome, right? Catalysts only make reactions go faster. They don't change the heats involved or the thermodynamics involved or the equilibrium involved. So that's what we see here. We've got two carbon-carbon bonds, and the stoichiometry, they're trying to show at the very bottom. The stoichiometry is we have 2 moles of carbon double bonds, and we're adding 2 moles of hydrogen, H2 molecules, and that gives us the same 2 carbon-carbons hooked together, only now with single bonds, and 4 carbon-hydrogen bonds. So I guess we could say that's also driven by entropy. Right? We start off with 4 moles and we end up with 6. All right. And I think this is what we're trying to show here too. If we oh, okay. All right. The one on the left, A, is this one. The B is this one. And I think the idea here is to say we could treat these as if we have 2 separate, if we compare the single hexene as the hex 1-ene versus the hex 2-ene, but we take the same stoichiometry, then C gives you the exact same heat as B. That's the takeaway from this slide. Let's see. All right. I don't need to spend time on that slide. We already covered that one. Now, what would happen with an allyl anion? Right? Remember what we were looking at earlier, where we had CH2 with a lone pair and a negative charge. That was our carbene. This is an extension of that. Only now we have incorporated into this group a double bond, so we can resonate with it. We have 4 pi electrons delocalized over 3 carbons, and we also get conjugation. Okay. This slide, say we substitute, instead of that carbon, we put an oxygen there. Can we still get a resonance hybrid that predicts conjugation? And it looks to me like we can, because we've got p orbitals that are parallel to one another, they overlap, and even though that oxygen has lone pairs, those lone pairs are stuck out there in sp2 hybridized orbitals. So this acetaldehyde is what we're looking at. Right. All carbons are, all 3 atoms, not just carbon, all 3 atoms, carbon, carbon, and oxygen, are sp2 hybridized. That frees up a p orbital for overlap. And we have sufficient electrons to go into that system. And since those lone pairs are perpendicular, they don't participate. That's another thing to consider. Is you don't necessarily have to have p orbitals available, but those p orbitals must also be parallel to their neighbors in order to overlap. Otherwise, they're isolated. All right. Oh, and again, an atom can contribute at most one lone pair of electrons to a particular pi system. And that's goes back to the fact that with a hybridized system, you can only have one possible parallel overlap, and the others are off axis, so to speak. All right. So now let's look at aromatic structures and try to extend what we know about conjugation so that we can look at aromatics. The story is told that this German chemist, August Kekulé, was struggling. In fact, the entire organic chemistry community was struggling with the fact that benzene was a known compound with that molecular formula, C6H6. And all kinds of structures have been proposed to account for it. Kekulé himself, the story is told, had a dream, had a vision, I think. It wasn't really a dream. He was awake, had a vision of this molecule, 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6. This molecule reaching around like a snake and grabbing its own tail and forming itself into a ring. And when he did that, then he could account for this formula. Right? Makes a nice story. I don't know if it's true. But what it does do for our discussion, and in fact, we've determined experimentally that the bonds between each of those carbons are exactly the same. Each one is exactly 139 picometers. All right. If we draw a resonance structure, how many resonance structures can we draw? Well, if we get our curved arrows in there and we move a double bond, move those electrons over to the neighbor, then if we do it like this, let's see, they start with that, that, and that. If we move these two over here and make a double bond there, that's 1, 2, 3, 4, and there's a hydrogen here. That's 5. We can't do that, right? So that means this one has to jump this way, and that forces this one also to jump that way. So we can produce only one resonance structure for benzene. Two. We can produce one alternate. So we can only have two resonance structures. And that's why very often you'll see benzene written like this. It just draws that circle in there. In a practical sense, this super stabilizes the molecule. Benzene rings are extremely stable. And in nature, I learned this in agronomy, soil microbiology. When a tree falls and it starts to break down, right? First thing that happens is insects go in there and rip it apart. Or in some cases, a woodpecker comes along. I had a stump sitting in the back of my yard after we cut down a tree that was threatening to fall on my neighbor's house. So this stump was sitting up about that high, and apparently it had been invaded by insects. And one day I heard this, it sounded like a jackhammer. And I looked out my back window, and there was this first one and last one I've ever seen pileated woodpecker, big guys with the big crest, red crest. He was hammering away at that thing. Well, that's the first thing that happens to a fallen tree or a stump. It gets physically taken apart. And then the stump or its branches or leaves. In fact, you could make this claim for just the leaves falling in the fall each year. The first thing that gets broken down are the functional groups, side groups. They get ripped off. And then most microorganisms have enzyme systems that will attack the single bonds, the easy bonds to get at. Then it goes after the conjugated systems. The last thing that's decomposed is the benzene rings, the aromatic compounds in there. And it's not just benzene. There are other aromatics that we're going to talk about in a minute. But the decomposition occurs in that order simply because it takes an enzyme system that's tuned to a particular molecular structure in order to break it down. And very few organisms have those enzymes for aromatic compounds. Okay, back to the topic here. So the electron delocalization involves all of the carbon atoms, and each one contributes a p orbital, and each one also contributes an electron. So each one of these carbons we could consider as sp2 hybridized in the valence bond model. And they form this donut. It's often drawn, if you take this molecule and tip it on its side, it's often drawn with a donut on top and a donut on the bottom to represent the electron density around the molecule. Forms a perfect ring. This is a cyclic pi system. In this delocalization, it's almost like, how do you rationalize this? Have you ever heard about superconductivity? Yeah, it's a characteristic of conductors or non-conductors, as a matter of fact. You get the temperature low enough, you can remove all resistance in the circuit. So once you get the electrons moving, they don't stop. They just keep going. So if you did that in this ring structure, those electrons would just keep doing that forever. No resistance. And that's the way I visualize the benzene molecule. Those electrons are just free to move, and they're very, very stable, lower energy. The molecule is symmetrical. It is planar. We know that from physical measurements. Each one of the bonds is equivalent in length and strength. And I've already mentioned this and put it in bold. These molecules, these benzene systems, are unusually stable, which means if we enter a benzene into a chemical reaction, the last possible reaction that's going to occur is something involving the carbons inside the ring structure, changing their relationship. Now, you may be able to attack and attach things on the outside, but you're not going to change any of the carbon-carbon bonds in that ring structure. And here's, okay, we're leading into that in just a minute. If we look at this 1, 2, 3, 4, 5, 6, 7, 8, let's see, 2, 3, 4, 5, 6, 7, 8, 9. 9 carbons in this one. What's the longest chain? It looks like 8 carbons long is the chain. And we have a dione, all right? Yep, at the 3 and 6 position. This is a symmetrical molecule. We have an oct-4-ene, all right? So it doesn't matter whether you count from the left or the right. And then the groups are opposite to one another, so it's an E isomer. and the let's see, the diones are at 3 and 6, and the methyl groups are at 2 and 7. Okay, now we got our bearings. If we react that with bromine, we can add bromine across that double bond. We can remove that double bond, and the bromines will be anti to one another. Okay. So, but if we take a benzene system and we apply bromine to that one, we get no reaction whatsoever. Right? Bromine will not add across any of those double bonds because, in fact, those double bonds don't exist. Right? They're not pure double bonds. They're hybridized. In other words, they're not full double bonds. So, in my way of thinking, if you just take two of those carbons on that benzene ring and you look at, what's the electron density, what's the possible negative charge there that would make them attractive to an electrophile, right? Well, they're not as dense because they're spread out, right? So when bromine comes in there, and we expect the bromine molecule to experience a momentary redistribution of electron charge and make one side positive and one side negative, it doesn't happen, and at least not as strong as it should be in order for the attack to occur. So that delocalization of electron density in the benzene ring system reduces the attractiveness, the electrophilic nature. What's required is a very, very strong Lewis acid. So tribromo, iron tribromide. What would that be? Iron 3? Iron 3. Yeah, iron 3 bromide. If we use that, then we can induce a substitution reaction, but it still will not attack double bond. All right, how about cyclobutadiene? In this case, it looks to me like all right, this is a puzzling statement. Resonance doesn't fully explain benzene's unusual stability. Conjugation does, but resonance itself doesn't. Well, resonance doesn't because this is resonance. That doesn't explain its stability. If it did, then we would expect a similar stability for cyclobutadiene. But we don't see that because the double bonds in that molecule are actually shorter than the single bonds. So if we resonate the molecule, we cannot produce a resonance structure that looks like the one on the far right. All right, so what's the key here? We have alternating single and double bonds. So we would expect, if this were a linear molecule, we would expect, say we broke the bond between A and D. Then we should get conjugation between A, B, C, and D, actually. Those 4 carbon atoms. We should get conjugation, but we don't see that in the ring structure. These molecules are unusually unstable. And part of the reason may be the bond angles. Right? What would be, if these were sp3 hybridized carbons, which it appears to be, what's the ideal bond angle there? If it's trigonal planar, the bond angle has to be 120 degrees, right? But that would be the bond angle if we had a carbon here and we had say double bond here like this. I'm just making something up. Then the bond angle here would be 120 degrees. Okay. But if you put these carbons in this square structure, what's the bond angle? 90 degrees. There's a lot of bond strain there that contributes to their instability. That's one of the explanations. It's probably not the only one. Aside from the physical evidence that the bond lengths are different, right? That clinches it there. Molecule is rectangular, right? Oh, they're not even going to finish it. All right. Well, I like my explanation. the bond angle's too narrow. There's a lot of bond strain in there. Now, if we looked at them, this should be a planar structure, right? So the possibility of overlapping pi. Oh, okay. The pi orbitals won't ideally overlap. Yeah, because if you get like this and like this, like these are close together, but these are too far apart. You don't get the pi orbital overlap that you're expecting. Right. So there are two explanations for this. One is the bond strain, and the other is the distance between the pi orbitals that are supposed to be overlapping. Okay, now we can go to discussion of what do we mean by aromatic versus anti-aromatic. Benzene is aromatic. Cyclobutadiene is anti-aromatic. And we're going to be introduced to a rule or a set of rules that help us differentiate between aromatic and anti-aromatic. So we don't have to fumble around. Aromatic compounds have cyclic pi systems that are unusually stable. All right, that's a blanket statement. They have to be ring structures. Anti-aromatics also are ring structures, but they're not stable. All right, so this is a practical definition. I mean, it doesn't get into the mechanics of why. All other compounds are non-aromatic. That is, they're neither unusually stable or unusually unstable. So they're in between. All right, so here's our benzene. And if we look at the heats of hydrogenation, benzene would be at a very low energy state. And we would get 206 kilojoules per mole released from the hydrogenation of this molecule. So that's less than than we saw before. Yeah. Cyclohexene, on the other hand, would let's see. Okay, we have to if we just use 1 mole of cyclohexene, we're comparing apples and oranges because benzene has 3 double bonds. Cyclohexene only has 1, so we need to use 3 moles of cyclohexene. And they are using a catalyst. How about that? And so we need 3 moles, actually 3 moles of double bonds to match the benzene. And when we do that, we find that the heats of hydrogenation for the cyclohexene is much higher per mole, quite a bit higher. So this is just an illustration of the stability of the molecule. Now, if we compare benzene hydrogenation with 3 cyclohexenes versus the cyclobutadiene versus two cyclobutenes, then we see that the heats of hydrogenation are reversed. In other words, we're starting at a much higher energy level with the cyclobutadiene. So when we hydrogenate it, we get more energy out of it. Right? It starts out higher, ends up at the same place as the cyclobutene. So 2 moles of cyclobutene will give us just a slightly, well, actually less energy than the cyclohexene. But it's the reversal. Right? What we're saying is that the benzene is aromatic and very stable, whereas the cyclobutadiene is anti-aromatic and very unstable. That's the whole point of that slide, I think. This is the same thing. I'm not going to stop here. Okay, here are the rules. And let's see, since that's got an umlaut over the U, it's probably pronounced Hückel. I'm not sure if Hückel is Scandinavian or German, but let's anglicize it. These are Hückel's rules. Okay, so if you start with a Lewis structure, and we're trying to determine whether it's aromatic, non-aromatic, or anti-aromatic, then we're going to end up with, has anybody had statistics here? Okay, so the one thing they drilled into our heads at the very beginning, the first course in statistics, is this A statistic that you're calculating. You calculate A statistics from a data set so that you can compare that value with some expected value. Right? And when you compare your calculated value with the expected value, then you can say what type of error is possible. It's type 1, type 2 errors. So that's what we're trying to do with Hückel's rules. We're trying to generate a number and then compare that to numbers that are characteristic of aromatic compounds, or numbers that are characteristic of anti-aromatic compounds, or those that are non-aromatic numbers. That's where we're headed with this. Okay, so a species is aromatic if the cyclic pi system, and these are all, they have to be cyclic, contains an odd number of pairs of electrons. These numbers of electrons are called Hückel numbers, odd numbers of pairs. So let's look at benzene, for instance. If we look at the Lewis structure for benzene, it's going to look like the single double bond here. So if we're using Hückel rules, we can use the Lewis structure. So this is going to say, look like that. All right. So how many pi electrons do we have here? We have 2, 4, 6. 6 pi electrons is how many pairs? Is 3 pairs. That's a Hückel number. So we would expect, well, the other conditions are the fact that it has to be a ring structure. It has to be planar, right? And it has to have a Hückel number, an odd pair of pi electrons. Anti-aromatics are also cyclic pi systems. They contain an even number of pairs of electrons. So when we looked at the cyclobutadiene, right, we had four pi electrons. That's two pair. That's anti-aromatic. Okay. So it satisfies the planar requirement, the cyclic requirement, but it fails with the numbers to be aromatic. So it's anti-aromatic. All others are non-aromatic. So in order to determine non-aromatic, you need something that breaks one of those three rules. Right? If it's not cyclic, then it has to be non-aromatic. If it's not planar, it has to be non-aromatic. Okay. For p atomic orbitals to be fully conjugated around the ring, the atoms that contribute to these orbitals must lie entirely in the same plane. Okay, no, rule number one. Right, I gave that one to you already. Each Huckel number contains an odd number of pairs. So 6 electrons is 3 pairs. That's for benzene, for instance. And that's a Huckel number. Okay. Anti-Huckel numbers are even pairs. Another way to calculate them is Huckel numbers correspond to 4n plus 2, where n is any integer greater than 0, greater than or equal to 0. So, yeah, if n is 0, you got 2. That's one pair. That's an odd number. If n is 1, then you got 4 plus 2 is 6. That's 3 pair. That's an odd number. Let's say, what if n equals 4? That's 16 plus 2 is 18. So that's 9 times 2. That's another odd number. Okay, so it works. Whereas anti-Huckel numbers are just 4n without the 2. Where n is any integer greater than or equal to 1. All right, so if we look at, we've already looked at benzene. We know that one is has the Huckel number. Cyclobutadiene, we've looked at that one. Hexane 135 triene. Now that's a conjugated system, but it fails because it's not a ring structure. Let's see. All right, there must be some circumstances where these rules fail. Otherwise, we wouldn't have to go into additional discussion here. Draw curved arrows to represent electron movement via resonance. Okay. Determine whether the species has a cyclic pi system. Yeah, fine. Not just cyclic molecule, but a cyclic pi system. Count the number of pi electrons used. Pi electrons, use the curved arrows you drew in. Okay, that tells you how many. All right. So if we do it that way, we end up with the same results for these three molecules. So we've got A is aromatic, B is anti-aromatic, and C is non-aromatic. Okay, here's where we get into trouble and sometimes questioning how this works is when we have a heterocyclic molecule like pyridine. Okay. 6 electrons occupy this cyclic pi system. The lone pair is isolated from the pi system because it's perpendicular. Right? That nitrogen is sp2 hybridized, but it has a lone pair that sticks out away from the ring structure. It's perpendicular to the ring structure. So we have 2, 4, 6. We have 6 pair. We have 6 electrons, 3 pair. That pyridine should be aromatic. What about pyrrole? Well, we have 6 electrons occupy this cyclic system because, the lone pair on this nitrogen is parallel with the rest of the pi system. So it contributes. And again, we have 3 pair. So pyrrole is also aromatic. What about furan? Furan has 2 lone pairs. One of them is perpendicular, one of them is parallel. So this one is also aromatic. Let's see. Oh, I got this one animated. I missed that. These curved arrows start on a bond and end on a bond. Yeah, that's right. If you're going to do this curved arrow technique, that the tail starts on a bond and ends on a bond. Or it starts on a lone pair and ends on a bond. That's the second one. Oh, curved arrow starts on a bond and ends on a lone pair. Furan. I guess it would have to, because you can't have 3 bonds to oxygen. Okay, so all possibilities. I go back to the Huckel rule. All right, how about these? This is cyclopentadienyl anion. 6 electrons occupy this cyclic pi system, aromatic. Now, how do we know that lone pair on that carbon is parallel with the other carbon p orbitals? Because that carbon, that anion, the negative carbon would have to be one, two. It would have to be sp2 hybridized in order to accommodate 2 bonds in a lone pair. That must not be the only lone pair. Yeah. Take time to draw that one out. All right, they're saying there's a lone pair here. But this has a hydrogen, that has a hydrogen, there's a hydrogen, there's a hydrogen. And if this is a negative charge, -1, carbon starts off at 4, so we need a -5 to give you a -1. So if it starts off at 4, we have 1, 2, 3, 4, and there must be another hydrogen here. Okay. It's unclear from that picture that we have like this, like that, and then a lone pair here gives it a negative formal charge. That means this bond, that bond, that bond makes this the sp2 hybridized structure on that carbon. And then the unused p orbital now contains that lone pair, and it's able to interact with all the other p orbitals. Does that make sense now? It took me a second to realize what was going on. They left the hydrogens out, and that is what messed with my head. How do you get this lone pair to overlap with these others? And you do it because this is an sp2 hybridized carbon with 1 bond to carbon, 1 bond to carbon, 1 bond to hydrogen. And the unused P is parallel to the others. Okay, so cyclopentadienyl anion is aromatic. How about cyclopentatrienyl cation? We have to do the same thing. Okay, we got 7. Yeah, hepta. We got 7 in that group. I don't know about you, but it helps me to do it this way. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. And we've got a positive charge here. And we've got a double, double, double there. Yep. Okay. We know all these have a hydrogen on them. And this one is a positive one. So 4 minus 3 give us a positive. So we can only have 1, 2. That would make this a free radical if I put just the third electron in there. 1, 2, put a third electron there. Unless that's a hydrogen. If that's a hydrogen, yeah, then it has 1, 2, 3. Okay, that makes sense now. So this is sp2 hybridized with 1, 2, 3 bonds, and that positive charge is located in the perpendicular or the unused p orbital that's parallel to the others. Okay. So instead of having the lone pair in there now, this is empty. Whereas these guys have an extra electron available. Okay. All right. And then we count them up, right? 2, 4, 6 is 3 pair. That's aromatic. Okay, how about cyclopropanyl anion? How about that one? Anion? Yeah. Lone pair here. That makes them negative charge. That means that has to have a hydrogen. That's a hydrogen. And 1, 2. See, that carbon, it's a -1. 4 has to be -5. 1, 2, 3, 4. There has to be a hydrogen here to do that. Okay. Now, that being the case, we do have that available, but do we have one available over here? Well, if we count up the number of electrons, we have only 2 pair. That's an anti-aromatic number. It's not a Huckel number. Okay, so I think again we're looking at bond strain, and the p orbital is not going to overlap. That's the only explanation I can think of. Bond angle, which is 60 degrees. Right, that's really strained. That's anti-aromatic. Determine whether this species is aromatic, anti, or non-aromatic. All right. So let's make room and see if let's use the rules first and see if we can figure this one out by the rules. Sulfur there, this, like that, there, there. And then we have here and here. Have a vinyl group on the side. Okay. And there's our lone pairs. We shouldn't have to deal with the hydrogens. Okay. Here's our ring structure. Right. We have, remember, we can only have one of these pairs can contribute to the structure. So we have 2, 4, 6. That's the Huckel number, 3 pair, 6 electrons. Okay, that's satisfied. It's a ring structure, and it should be planar. So this is probably aromatic. Let's see. Okay, they're using curved arrows. Can you draw curved arrows to represent the movement of electrons completely around the ring? Yes, you can. Does the molecule have a cyclic pi system? Yes, it does. How many electrons in the pi system? 3 pair. Okay. So that one should be, let me see, I've got myself blocked off here. So this should be aromatic. Yeah, the ring is aromatic. Okay. Aromaticity in larger rings. In annulenes. Annulenes are monocyclic, one ring molecules that contain only carbon and hydrogen, consist of alternating single and double bonds completely around the ring. All right. So benzene is 6-annuline, cyclobutadiene is 4-annuline. All right, but they're not necessarily aromatic. If we look at this stop sign, right, this octagon, we have an 8-annuline. Should it be anti-aromatic? If it's planar, has to be planar first. Right? As it turns out, it's not planar. It's tub-shaped. The reason it's tub-shaped is because of the hybridization required gives us a puckered structure. So it fails in being non-planar. Now, how do you figure that out? Just by looking at the structure. Because it looks like each one of the carbons is sp2 hybridized. It should be 120 degrees bond angles. I can't figure that out from the A structure. You have to be told. And besides that, if it has 2, 4, 6, 8, it has 4 pairs, that's anti-aromatic anyway, right? Whether it's planar or not. It's got the wrong Huckel. It's got the anti-Huckel number. But the explanation is that since it's this boat structure, then you don't get overlap of the p orbitals. Okay. How about multiple ring structures? The one on the left is biphenyl. In other words, there's only a single bond between the carbons. So I look at it this way. You've got a benzene ring here. And we can do it like this. And then instead of a hydrogen here, you have another let's try this. Did like that, that, that. There we go. So let me see. I'm going to put them in the same place as they did. No, not exactly, actually. Okay. These are 2 separate aromatic systems. They, if these were linear, then we would expect them to be conjugated through here. But aromatic systems don't do that. This bond is free to rotate right here. So it's not going to allow pi orbital overlap, p orbital overlap. Right? So you have 2, the biphenyl has 2 aromatic systems connected by a single bond. All right. When 2 rings share 2 points of contact, you have a fused ring. And that's what naphthalene is. Anybody know what naphthalene is used for? forget what the proper name is, but it's you put it in your cedar chest to keep the moths out. Naphthalene is one. There's another compound that escapes me for the moment. But now we have a fused ring structure, and that means that both rings are in the same plane. And then we can count up the number of pairs of electrons: 2, 4, 6, 8, 10. 10 is 5 pairs. That's a Huckel number. So the naphthalene is a complete aromatic double ring structure. Anthracene, and a lot of these compounds, particularly the naphthalene and the anthracene and the fused ring compounds, you can find those in coal. I think that's where they were originally isolated, because coal undergoes what we call pyrolysis. In other words, it's just subject to heat, and when it's buried in the ground, there's no oxygen. So it doesn't oxidize. It doesn't form carbon dioxide. So it just breaks bonds. And these are some of the products that you get out of it. So on the right hand, the anthracene, let's see, 2, 4, 6, 8, 10, 12, 14. That's 7 pair. That's a Huckel number. So both naphthalene and anthracene, their fused aromatic systems it's one complete aromatic pi system for each one of them. How about this one? This is a fused system, right? So let's see. Does the molecule contain a cyclic pi system? Yep. Oh, how can you tell? How can we tell? That's a good question that I don't have the answer to. Maybe it's in the book. Or it could be in the notes that accompany each one of the slides. I just missed them. You know that I'm going to do that. Hold on a second. I have to stop the share to do this. So let me look at let's go down to keep going till we get to getting close. Here we go. Now, how can you tell? Oh, that doesn't, okay. The instructor's notes don't help out at all. All right. Never mind. Let me reshare this. Let's see if I can find it again. There it is. I guess for the moment, we're just going to have to take it on faith. But I think I can't justify saying that simply because they're fused, that they're in the same plane. Because I can envision possibilities where you get fused rings that are not in the same plane, especially where you have bridge structures. But if we assume that they're in the same plane, then we count up 2, 4, 6, 8, 10. That's 5 pair. That's a Huckel number. This should be an aromatic molecule. Okay. So a deeper look. Principles of molecular orbital theory. Okay, these are just reminders so that we can transition from valence bond theory into molecular orbital and hopefully answer some more questions. Remember that the number of molecular orbitals will always equal the number of atomic orbitals that go into the mix. That's a hard and fast rule. we produce a new set of molecular orbitals derived from the atomic orbitals, and the atomic orbitals go away. This occurs by constructive interference and destructive interference. Constructive interference gives us bonding orbitals. Destructive interference gives us anti-bonding orbitals. And we can predict a node. In other words, a node is where you do not expect electron density at all. We can predict a node where complete cancellation of the resulting molecular orbital occurs, and there's zero probability of finding electrons at that location. So when we draw an orbital, say like this, there's your node right there. We're saying electrons will not occur at that point. They may occur in these regions, but they don't occur at the constriction of that particular figure 8 that I just drew. All right. So here's some helpful hints for deriving the molecular orbitals of an acyclic pi system. Acyclic pi system, we're talking about conjugation. Draw the lowest energy pi molecular orbital. The lowest energy pi molecular orbital. Here, all contributing atomic orbitals have the same phase. Only constructive interference takes place. So mixing produces no new nodes in the pi molecular orbital. Draw the next lowest energy pi molecular orbital. For this molecular orbital, the p atomic orbitals contributions will lead to one new node on mixing, and the phases of the contributing atomic orbitals must change on crossing the node. Okay, I think we're going to need pictures to make sense of this one. Draw the next lowest energy level, and okay, so what we're trying to do is draw a potential pattern for molecular orbitals and identify where their nodes occur so that we can say something about potential overlap. All right, we'll come back to this slide, but I think we need a picture. Here we go. So if we start at the bottom and we say, okay, we've got these 3 carbons and we've got the p orbitals that can go into the system. Right? So each one of these carbons has a p orbital available. Constructive interference for this this pi 1 representation allows for constructive interference for all 3 of those carbons. And that produces the molecular orbital system you see on the right. If we go to the next level and we introduce a nodal plane, the nodal plane occurs on the carbon. That's because we can only have one nodal plane for the next, the pi 2. Then you get these separate, they're separated molecular orbitals, one on the left and one on the right. There's no contribution to the pi orbital. If we introduce 2 nodes now, so we're adding a node. We added a node, now we're adding 2 nodes. Those 2 nodes occur between the carbons. So that means that we have destructive interference at the nodal plane, and that separates all the carbon atoms. So there's no molecular orbital overlap there. We have 2 nodes. Okay, so let's go back and see rules for adding nodes. All right, so what we've just done is what these rules cover. For a symmetric molecular species, the nodes must be placed symmetrically. If there is an odd number of new nodes for a particular molecular orbital system, then one node must appear at the center of the species. And that's why our first one was on the atom. For any node located on one half of the species, there must be a corresponding node located on the other half of the species. So each node in the pair is the same distance from the center of the species. So when we created our third one, that's why we had to symmetrically place a node there. And whenever you cross the node, you flip the polarity of the pi bonds. That's why on the bottom there are no nodes. So all of the p orbitals are blue on top, white on the bottom. We introduce one node, then we have blue on the top and blue on the bottom on the other side of the node. And it just keeps going like that. Every time you cross a node, you have to flip the polarity. Okay. So here's the molecular orbital energy diagram for the allyl cation. On the far left, we have non-interacting atomic orbitals for each of the carbons. And the first pi system is on the bottom at the lowest energy. Now, the lowest energy has no nodes, and we get bonding interaction. And that produces a pi 1 bonding molecular orbital. If we put the node on the carbon in between, then we get a non-bonding molecular orbital. Right? There's no bond between the two. If we get two nodes, now we have on adjacent carbons, we have an anti-bonding molecular orbital because the polarity of the p orbitals, it flips each time. So what that does is it increases the energy of that orbital. And all of those together describe that pi anti-bonding orbital. All right. This hasn't helped me much yet. I'm hoping that this is preliminary stuff and it's all going to come together. Each sigma bond in a Lewis structure represents a pair of electrons occupying a sigma bonding molecular orbital. Okay. And there is one sigma star antibonding molecular orbital for each sigma bonding molecular orbital. All right, that makes sense. I think what the author is trying to do here is simplify so that we can actually use molecular orbitals in describing our molecules rather than having to go back and draw from scratch, which is difficult to do for complex molecules. So we've got these simplifications that are helping us. It's kind of like when we do mechanisms, right? We simplify by eliminating the spectators. Then lastly, the sigma molecular orbitals tend to be lower in energy than the pi molecular orbitals, whereas the sigma star molecular orbitals tend to be higher in energy than the pi stars. That reminds me of atomic molecular orbitals, where we drew, we had the sigma here, we had the pi here, then we had the pi stars here, and then we had the sigma stars here. Right? That's with no sp mixing. That's the way it would look. So the same concept is being used for these more complex molecules. All right. So we've got 7 sigma molecular orbitals and 7 sigma star molecular orbitals. Now, let's see if that comports with the number of bonds we have in the molecule. We have 1, 2 between the 3 carbons. 1, 2, 3, 4, 5, 6, 7. Yeah. We have 7 single bonds in this molecule. So we have to have 7 sigma molecular orbitals and 7 sigma star molecular orbitals. And then we have, let's see, we have, how do we get 3 pi orbitals out of this? I'm gonna have to go back. Hold on a second. Okay, here's how we get 3 pi's out, pi molecular orbitals out of this. Because we have 3 carbons that are contributing individually a single p orbital. So those 3 p orbitals can be arranged in these possible ways. We can have all of them phased together with no nodes. We can have them opposite phase with a node in between on an atom, or we can have 2 nodes with alternating phases. So that gives us, because we have 3 carbons contributing p orbitals, we get 3 pi orbitals. 1 bonding, 1 non-bonding, 1 anti-bonding. Now, if we had 4 carbons in a conjugated system, it would be just that much more complicated. And here we go. Now we have 4 carbons with a conjugated system. We have a total of how many valence electrons? Well, let's see. Hydrogens, we have 1, 2, 3, 4, 5, 6. So that's 6 electrons for hydrogens. We have 1, 2, 3, 4 single bonds with the carbons. 3 for the carbons. So that's 3 times 2 is 6. So how many have I got so far? 12. And then we have 2, 4 for the double bonds. 4 and 12 is 16. Okay, I'm missing some electrons. Let me draw it on the board. One, two, three, four. Like this, like this. And we have, let's see, 1 hydrogen there. We have 1, 2, 3, 4 hydrogens here, 1 here, and here. Okay. Let's try it a different way. How many electrons do we have we're talking about here? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. That was simpler. 22 electrons that we have to place into this molecular orbital system. All right. We've got how many sigma molecular orbitals? Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 sigma orbitals and 9 sigma star orbitals. Now we have 4 carbons with a p orbital each. So we have, if we have no nodes, they're all phased together. We have that bottom one at the lowest energy. So that's pi 1. Pi 1, no nodes. Okay. What about pi 2? It has to be symmetrical. So we have to put a node between, we have 2 carbons and then 2 more carbons. And the phase must shift across that node. Right? So we have 2 on the left are in phase, 2 on the right are in phase, and the 2 in between are out of phase. So this is pi 2 with 1 node. If we put 2 nodes in there, then they have to go, to be symmetrical, they have to go between the 1 and 2 and the 3 and 4 carbons. And you see the phase shift appropriately. Right? So this pi 3 has 2 nodes. Okay. How about pi 4? Pi 4 has the maximum number of nodes, a node between each carbon atom, and the phase shifts between each one. Right? So this pi 4 has 3 nodes. All right. How do we call these? This is definitely bonding because they're all in phase. We still get bonding here because we have available 2 carbons in phase and 2 carbons on the other side in phase. So this is a bonding molecular orbital. How about if we have 2 nodes? If we have 2 nodes, then, well, we have 2 nodes. They're saying that's anti-bonding. But those carbons in the middle are in phase. So why don't they bond? That's puzzling. The author's calling this anti-bonding. It may simply have to do with energy, right? Because that's higher energy than the original atomic orbitals. And then obviously 4 is anti-bonding. Okay. So if we put in the number of electrons, we have 22, right? So we have 9 sigma orbitals. How many electrons will that accommodate? This is 18 electrons, right? 2 for each orbital. So that leaves us 4. So we're going to have we're going to have 2 here and 2 here. 2 here. There we go. So we have 2 bonding here and 2 in the bonding here. And this one, these are empty. And all of these are empty. So this one is the highest occupied molecular orbital, and this is the lowest unoccupied molecular orbital here. All right. Now, where does that get us? The Frost method for energies of cyclic pi molecular orbitals. Okay. So what we're going to try to do is on this diagram superimpose the cyclic structure. That's the Frost method. We orient one vertex of the polygon directly downward. Doesn't matter which one, you just pick one. Then we add the non-bonding energy orbitals, draw a dashed horizontal line through the center of the polygon, which represents the energy of the non-interacting p atomic orbitals, and place the energies of the pi molecular orbitals, draw a short, solid horizontal line at each vertex of the polygon. Okay, so this is what benzene would look like. We direct the one apex down, right? And that's the first bonding orbital. And then the 2 and the 3, well, see, we have a different set now. This was for 4. If we do it with the cyclic ones, then we have what? 1, 2, 3, 4, 5, 6. We have 6 possible pi orbitals. And I think the reason that we want to use the Frost method was created was because these linear conjugated systems work well here, but it's difficult to tell where the nodes are and where the bonding orbitals and where the anti-bonding orbitals are for cyclic systems. So that's where the Frost method was developed. So we position this 6-membered ring with one of the apexes pointing down, and since we have 6 systems, we're going to have 3 bonding and 3 anti-bonding in this case. And the reason for that, and the reason we don't have any non-bonding orbitals is in this Frost method. The non-bonding would be on that atomic energy level line. Okay. And we don't have any there because of the symmetry of the molecule. Puts 3 above and 3 below. So for benzene, we only have bonding and anti-bonding. Okay. So far, so good. Okay. And then we count up the pi electrons, right, which will be, we're in chapter, what are we? Chapter 14? Yes. Yes. We're going to try to get both of them in. Um, we might have a few minutes. We should at least go check it. Right. I've looked at it this morning and it's kind of congealed. Right. So it may take a little longer, but we can assess that when we get back there. So this is for benzene, and this is the Frost method, and this is what it looks like. So I think picture's worth 1,000 words. We've got 6 p atomic orbitals going to 6 pi molecular orbitals. And the number of electrons that have to be accommodated now are, if we count up the pi orbitals around this structure, we have 2, 4, 6 electrons. So we put those 6 electrons in the lowest energy orbitals, right? We use the, and my mind's gone blank again. Aufbau principle, where the electrons go in lowest energy first, and then we stack them up next highest energy. And that's what the benzene would look like. Cyclobutadiene, though, would come later. Because I don't see cyclobutadiene. It must be later. So we're going to talk about benzene some more. Okay. Well, that's the fact that the energy level of each molecular orbital rises with each additional nodal plane. That just simply makes sense based on the situation. So pi 2 and pi 3 are going to be at the same energy level, and pi 4, 5, and 6 are going to be much higher energy levels, and we're adding nodal planes. So what that tells me is that pi 2 and pi 3 have the same number of nodes, only they're in different positions because we've got more carbons now, and you can draw symmetrical positions for those nodes. Different positions will give you the same energy, the same number of nodes. So this is what it would look like in picture form, right? At the very bottom, you have everything's in phase with no nodes. Then for pi 2 and pi 3, we can put a node across between 3 carbons in one plane, or we can shift that plane around and put we have to be symmetrical, right? So if we draw the structure like this, right, like that, and that, we can either put a plane through here, and that puts 3 carbons here and here. This is a node. Or if we put it through here, right, it's just the same thing. We just rotated the molecule. So the only unique node position we can use for benzene is through the atoms themselves. And that puts 2 on this side and 2 on that side. So with a single node, pi 2 and pi 3 are at the same energy level. Then if we do a similar type of introduction of 2 nodes, then we get pi 4 star and pi 5 star. And then if we put 3 nodes in there, that separates everybody from each other, and that makes the pi star 6. Okay, now butadiene, cyclobutadiene. I'm going to use a rag. If I go with that black eraser too much, it leaves a shadow. and microfiber will take it all out. Okay. So if we use the Frost method here for cyclobutadiene, right, one apex has to point down. So what that gives us is one bonding pi orbital, two non-bonding pi orbitals, and one anti-bonding pi orbital. And if we take, if we take the number of pi electrons, which would be 4, right? In the simplified version, there are 2 double bonds, so that's 4 pi electrons. And now we put them in there. 2 go into the pi bonding orbital, and 1 each for the pi 2 and pi 3 non-bonding orbitals. Right? And that's, let's see. I was trying to think of the rule, the name on the rule. It escapes me. We can't pair up electrons at the same energy level until we put 1 in each energy level. But I can't remember the name of it right now. Okay. So that doesn't explain why it's anti-aromatic to me. Is this going to explain why it's anti-aromatic? Well, this shows us why we have two non-bonding orbitals, pi 2 and pi 3. Pi 4, okay, that makes sense. I would expect with a single node. Oh, okay. For the non-bonding orbitals, if we put a nodal plane between 2, right? The only way you can put a nodal plane in that molecule is to separate 2 carbons on one side and 2 on the other, so they can overlap. That produces a pi bond on one side and a pi on the other side. If we rotate it 90 degrees and put the node in there, we've still got 2 on one side and 2 on the other, so they're at the same energy level, but they're also at the same energy level as the original valence bond molecule, because now we have a pi overlap on one side and on the other side, which is the same as the molecule that we're given. So that's why they're non-bonding. They're exactly the same as the original molecule structure. Whereas if we put 2 nodes in there, now we've introduced, they're all out of phase with one another. You don't get any overlap for the pi orbitals. Those are anti-bonding orbitals. I hope that made sense. Okay. Let me look at my hard copy and see where are we at. We ought to be getting close to the end, right? Got four slides to go. Okay. Aromaticity in DNA. All right. Why would aromaticity be a valuable commodity for DNA? Well, in a word, stability, right? DNA has to be stable across many generations of cell division. And DNA's information, let's see, there's another word for it. DNA carries data. it carries information from one generation to the next, and it needs to be reproducible and reliable from one generation of cells to the next. And in order to do that, we need stability so that the sequence, the code, the codon can be maintained from one generation to the next. And if you've got aromatic bases in there, then you stabilize those structures. So guanine, adenine, cytosine, and thymine are all aromatic molecules. Let's see. Guanine and adenine are the oh, mine's gone blank again. But they all have odd Huckel numbers. They have Huckel numbers, which are odd. And the base pairing required, how do the bases pair up? Got that? Go back. The bases pair up by hydrogen bonding. So the adenine pairs up with the thymine. Adenine A pairs up with the thymine by hydrogen bonding, and the guanine pairs up with cytosine by hydrogen bonding, and guanine will not hydrogen bond with adenine, and cytosine will not hydrogen bond with thymine. That's how we keep that. That's how the molecule retains its integrity, by not getting confused. And those base pair sequences, the sequences are what contains the information that's carried from one generation to the next. Oh, there it is. There's your hydrogen bonding. And because these molecules are, since they're aromatic, they're also planar, then those hydrogens and oxygens or hydrogens and nitrogens always line up correctly. Okay, well, this is repeating what I've already said. Each base pair is planar. It allows for efficient packing in the double helix. Who gets credit for discovering the double helix structure of DNA? You can use their last names. Watson and Crick. They got credit for, and the Nobel Prize for elucidating this. Who actually did the footwork? I can't remember her name, but it was a woman. And she did the X-ray crystallography for them. But unfortunately, she died at a very young age. And by the time the Nobel Prize was awarded, she wasn't even alive. So that may have been one of the reasons she was left off. And the other reason might have been just pure blatant misogyny. Okay. So the close packing of this information allows for all that information to be contained in the nucleus of the cell. And then, not only that, by that close packing, you get the ability to get some interaction between the bases as well. And that further stabilizes the molecule until it's ready to open up and be decoded.